Welcome to qnawire.
So now we'll work on problem 56 from chapter 20. In this problem, we're asked to use the standard reduction potentials listed in Appendix E and calculate the equilibrium constant for each of the following reactions at 298 Kelvin. So the first reaction is the oxidation of copper with silver cation. So we have two half reactions here, which we can look for in Appendix E. The oxidation of copper from copper to copper 2, and the reduction of silver from silver plus to silver neutral. So the first thing that we need to do to calculate the equilibrium constant is to get the potential or the EMF value. And so we do that by putting the reduction, which will be the silver reduction potential, minus the reduction potential for the oxidation half reaction. And when we do this calculation, we get 0.46 volts. So after we get the E, or EMF, we can calculate delta G through this equation here. And so we have a 2-electron reaction. So we have -2. 2 is the N value. The Faraday's constant is 96,485. And our EMF value, or E value, is what we just calculated. And so then we get -8.9 times 10 to the 4th when we do this multiplication. Then we can use this delta G value to get the K value, the equilibrium constant, which they're asking for. So we have ln K equal to delta G over -RT. So we have -8.9, the value we just calculated, times 10 to the 4th joule per mole. We have -8.314 joules per Kelvin per mole. And we have our temperature, which we're told is 298 Kelvin. And when we do this, we get a value of 35.8. So to calculate K, we have K is equal to E to the 35.8. This is the inverse ln. And we get a value of 3.16 times 10 to the 15th power for part A. For part B, the reaction which we're given is the reduction of cerium with bismuth solid. So we have the reduction of cerium and the oxidation of bismuth. So we look for these particular half reactions in Appendix E. So the reduction of cerium from cerium 4 to cerium 3 gives a reduction potential of 1.61, and the oxidation of bismuth is positive 0.32. So we subtract it, and we get a value of 1.29 volts. So delta G for this reaction will be this E value multiplied by Faraday's constant and the number of electrons that are transferred, which for this reaction is 3. Faraday's constant is 96,485. E is 1.29. So our delta G value is 3.73 times 10 to the 5th joule per mole. Then we calculate K. ln K is equal to delta G over -RT. We have our delta G, which we just calculated, 3.73 times 10 to the 5th. 8.314 for our gas constant and 298 for our temperature, and that gives a value of 151, which we can take the inverse ln, or the E, to get K is equal to 3.79 times 10 to the 65th power. For part C, the reaction which we're given is the N2H5 plus reaction with iron cyanide. So in this case here, the iron cyanide complex is being reduced, and the N2H5 plus is being oxidized to N2. So we can go ahead and look for these reactions in Appendix E, and we see that this reduction of this iron complex is 0.36, the potential, and the oxidation of this N2H5 is negative 0.23. That's the reduction half reaction. So when we add these up, we get 0.59 volts as our potential. Delta G we calculate in the same way as we have done previously. So in this reaction, we're having 4 electrons transferred based on the stoichiometry. And when we do this multiplication, we get a value of 2.3 times 10 to the 5th joules per mole. And using this, we can calculate K, as we've done previously. So these values should be negative because of this negative here. And we get a value of 92. So when we take the when we set this number to E, we get 8.21 times 10 to the 39th power as our value for K.